When going through your charts in your momentum lab, you've noticed that the impulse of the red ball on the green ball is always equal to an opposite of the green ball on the red ball. And you're like, well, why is this and what does it mean? You also notice that the momentum of the entire system was conserved, meaning that if you took the initial momentum of the red ball and the initial momentum of the green ball and add them together, that would give you the same value as the final momentum of the green ball added to the final momentum of the red ball. So these two facts must be connected in some way, and I'd like to show you how that is. Okay, so what we'll do is we'll start with these impulses, and we'll write out what the details of what an impulse is. An impulse is a force of red on green, and it's going to be equal and opposite to the force of green on red. How do we know this? That's Newton's third law. Every action has an equal and opposite reaction. If we take each of these forces and multiply by the time in which they are touching each other, then it gives us impulse. These time values must be the same on each side for algebra reasons and conceptually. The red ball and green ball can only contact each other for the same amount of time. I call that the touching principle. From here, you can replace an impulse to the force the red applies on the green. The impulse of the red on the green will change the momentum of the green ball. Because remember, impulses change in momentum. And the impulse from the green ball will change the momentum of the red ball. Now we can expand on what a change is, and don't forget our minus sign here. A change is final minus initial. So we can move our terms around to put this negative inside our parentheses. So it will have negative P final and positive P initial. And now remember, what we've discovered in our lab is that total P initial equals total P final. So let's put all of our initial terms on one side. So let's add P initial to this side. And then we add P final to the other side. And we end up with these expressions that the final and initial momentums are equal to each other. Another way to write this is picking up here, saying, okay, well, let's go ahead and add this change to the other side. So you'd have 0 equals the change in momentum for the green ball and the change in momentum of the red ball. What this is saying is that the total system, which is both balls together, have no external impulses. They apply an impulse on each other, but when you consider them as a whole, there is nothing outside applying a force on them. Therefore, the momentum of the entire system is conserved, because there are no external forces if you group the red and the green together. So impulse is change in momentum. If we make our system big enough to include momentum of the whole system, then we can consider the conservation of momentum as long as there are no external forces. I'll show you some examples. So we're going to apply the conservation of momentum principle to some problems below. Conservation means that a quantity is the same before and after. Conservation of momentum means that the momentum is going to be the same of the whole system before and after, meaning the sum of both objects' momentum, momenti, octopi, this before the collision is going to be the same of the sum of the momentum afterwards. So we're going to add the MV values of each object before and the MV values of each object after, and they will always be the same. That's the conservation of momentum. And so in order to figure out what the before and after is, we need to identify an event. Normally this is a collision or some sort of dropping or hitting. And we need to make sure that we understand what parts of our event we will write out the momentum for, what are our pieces of our system, and that there are no external forces to our system, so that when we add all the momentums together, then there's no external forces to change that momentum. So we're treating all the impulses as internal, meaning that if you look at the orange and the brown car, the orange car will hit the brown car, and the brown car will hit the orange car. We're going to ignore the friction on the wheels. There is no other external aspects to this problem that will change the velocities of these cars. We're going to ignore air resistance, so there's no external forces, just orange on brown and brown on orange. The event is when they collide, when they hit each other. So this is where we consider the event. So we're going to have orange plus brown is going to equal at the end the new orange motion and the new brown motion. This is just like the balls, the red ball and the green ball, but now we're going to do it with two cars. So this is this term for sum, the sigma sign. So we're going to add all the momentums before the collision equal to all the momentums after the collision. So here's what it's going to look like. We're going to take the mv of the orange car. We're going to add it to the mv of the brown car. Then they're going to collide. Now we're going to take the mass of the orange car, which is the same, but a new final velocity, and we're going to add that to the mass of the brown car, which is the same, but a new final velocity. And so we'll fill those numbers in now. 15,000 times 20 plus 1,000 times 10 equals, then they stick together in the end. So we have the mass of 15,000 and the mass of 1,000 all stuck together with some final velocity. So we're just kind of combining these terms together to say there's one v final value. So let's solve for that v final just using algebra. We get a final velocity of 16 meters per second for the combination of the two moving forward. So the orange car slows down and the brown car speeds up, and that makes sense. Conceptually, all the numbers are positive, which means the objects were moving to the right and they're continuing to move to the right after the collision. Let's try this again over here. So we're going to assume again that they move off together after colliding. There's no external forces. Our system consists of both cars, orange on brown, brown on orange. So we'll just go skip right to filling in their momentums. So we're going to say P initial equals P final, P before the collision equals P after. So mv plus m. Now notice the v is backwards. It's really important, right? Now they're going to stick together, so we'll just take that total final mass and we'll have a final velocity value. Now let's go ahead and use algebra to solve for our final velocity. So in this head-on collision, the final velocity comes out to be -2 meters per second, which means the combined cars move off to the left. The last thing we can do in looking at collisions is we can label like the type of collision it is. From your lab, you know you can have a collision where your elasticity slider is at 100%, meaning they bounce and energy is conserved. Your elasticity slider is at 0, meaning they stick together. It's totally inelastic, perfectly inelastic, or somewhere in between, just called regular inelastic. And so in this case, our cars stick together under both cases. So in both cases, these are perfectly inelastic collisions. PIE, perfectly inelastic. Those stick together at the end. The maximum amount of kinetic energy is going to be dissipated from this system to other things like noise, deformation of the surfaces, heat, and so on.